Today in class we took notes on this slide, and we were talking about physics in general, and physics is the study of motion. So we had 3 questions about motion that you should have been able to answer by the time you left class. You should know how you know when something is moving, you should know how you measure motion, and you should know what causes motion. So ask yourself right now, see if you can, without looking at any of your notes or anything, see if you can right now just write down what those 3 things are before I go over them. You can pause the tutorial and then watch again. Okay, so how do you know when something is moving? Well, the best way to be able to tell if something is moving is to have a reference point. So all motion is relative, so you have to know what you're comparing the motion of the object to, and that would be your reference point. When something moves, it changes position from one place to another, and you can only tell that you've changed position if you have background to compare it to. All motion is caused by forces. And in this rest of this tutorial, I'll talk about the 4 different forces that can cause motion. And then finally, how did we measure motion? Well, we actually looked at 3 different measurements of motion in particular. So let's look at those together. Here are the 3 ways that we're going to measure motion in this class. We're going to measure speed and velocity, which are really the same thing except that velocity happens in a particular direction. So speed and velocity, though, have the same formula. You take the change in distance, divide by the change in time. In class, I talked about the fact that these little wacky-looking triangles are actually the Greek letter delta, and they mean the change in. Oh, the change in. And it's the change in whatever comes after it. So up here in the average speed formula, the change in distance is what we're looking for the first part of that equation. So in order to find the average speed of an object, you need to know how much distance it covered. What is the total change in distance? And then you also need to know the total change in time, how much time passed. And then you divide. You take the change in distance and divide by the change in time. And that gives you the average speed. So you can see delta is used in all 3 of these equations. And like I said, velocity and speed are both the same formula, but when you're talking about velocity, you want to include what direction you're moving in. Acceleration is the change in velocity. So that equation takes the change in velocity over time. So the units, we went over the units for speed and velocity in class. We said that they would be meters per second, m/s. For acceleration, your units are going to be meters per second, because that's velocity, divided by seconds. And because that looks weird, scientists have a shorthand way of writing that. So we write it like this: meters per second squared. Now you might be wondering, where'd the squared come from? Well, it's a math thing. I can show you in class where it comes from. But probably the easiest thing to do right now, before your brain gets full, is just commit to memorizing this. Units of acceleration, the label that you'll use, is going to be meters per second squared. You can also write it meters per second if you want to. Okay, so those are the 3 ways that you can measure motion. Let's take a second here and talk about the difference between average speed and instantaneous speed. In class, I ran a cart down a ramp, and I asked you guys to time it with your iPads, and then I measured the length of the ramp. And we found the average speed of the car as it went down the ramp. But then I asked you, does that speed that we just got, does that represent the speed that you would see on, say, a speedometer if you were actually driving that cart down the ramp? If you were a little tiny person inside of the cart and there was a little speedometer on the dashboard that you could check your speed every second, would it read whatever we got for our average speed the whole time, or would the speed be changing as the cart came down the ramp? So remember, your cart's going down a ramp. So the question is, as your cart goes down that ramp, does speed remain constant? Is it the same, or is it changing? And you guys all told me that, well, gravity's pulling it down, it should be picking up speed as it heads towards the ground. And that's true. we can't measure that with a ruler and a stopwatch because we can only get the change in time and the change in distance. We're not able to get the exact time and exact distance every step of the way. But these tools can. Your speedometer in your car is designed to be able to find that out for you, what exactly distance and time you're at any moment in time. And we're going to use in this class the motion detector and LabQuest devices, which work together to provide us with real-time data about where an object is. I also mentioned in class that our motion detectors, which you see one down here at the bottom, work by emitting sound, and that's why you heard all those clicking noises in class. So the motion detector goes click, 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 was driving everybody crazy in class. The same process is used by police officers who have what are called radar guns. This emits a type of sound wave also that comes out, and actually it emits something else, but it's the same principle. So what it does is it sends a wave towards a car, bounces off the car and comes back to the man and tells him how fast that car is moving. Bats use this technique. It's called echolocation. Echolocation. So in order for the bat to detect where that bug is over here, what the bat does is it sends out clicking sounds, a little more high-pitched than our motion detectors, and those clicking sounds travel away from the bat. They're called sonar, and they're the yellow lines. And when it hits the bug, that sound bounces off, it echoes off of the bug back to the bat. And the bat can tell exactly where that bug is by the direction that it comes in at, and also by how quickly it gets back to them. Your motion detector does the same thing. It sends out a cone of sound waves. And those sound waves then bounce off our moving object and tell the motion detector where something is. Which is why when I ran the cart down the ramp, I had a white index card stuck up out of it to pick up the sound waves and bounce them back. This slide is just a quick reminder of the difference between speed and velocity. Same formula, get the same numbers, but speed does not include direction. Velocity does. Velocity can be, you can give the direction by east, west, up, down, left, right, but very often in a physics class like this one, you're going to use positive and negative. So there's the positive direction, which would be moving in one direction, and the negative direction, which is the other way. And it doesn't really matter which is which. It's just a way to differentiate between two different directions. We also talked in class about acceleration and the fact that there's 3 ways to accelerate. And I'm showing you the 3 ways in this picture. Up at the top, this car starts out moving 30 kilometers per hour, and then after a little time goes by, it's moving 60 kilometers per hour. So the speed increased. So if you speed up, that's a form of accelerating. In the second picture, the car was starting out at 60 kilometers per hour and ended at 60 kilometers per hour. So it didn't speed up, it didn't slow down, but it did change direction. And when you change direction, you are accelerating, because acceleration is a measure of the change in velocity, and velocity includes direction. The third way to accelerate is actually to slow down. So you can go from 60 to 0, so you're slowing down, and that's a form of accelerating. In everyday language, you might say decelerate, and that's okay. But technically, slowing down and speeding up are both accelerations. Here's a great example of the fact that motion is relative. Notice that the person standing on this moving train car doesn't feel like she's moving, but the person standing outside the train car, to them, this person's moving really fast at like 80 miles per hour. So motion is relative. How fast something seems to be going depends on what you're comparing it to. If the person inside the car is comparing it to the wall behind her, she's not moving. But compared to the scenery outside, she is moving. So motion is caused by forces. And believe it or not, there's only 4 different forces in the entire universe. And it's even easier than that because these two up here, the strong and weak force, only happen inside of atoms. And so in a physics class like this one, we don't even need to think about those two forces. We'll talk a little bit about them when we do chemistry. The only two forces you need to worry about are gravity and electromagnetism. And I'll talk way more about both of those when I see you in class. So all you need to know is that any motion that you see in the everyday life is either caused by gravity or by this thing called electromagnetism. So when I push a pen across a desktop, it may seem to you like, well, that's the force of you. But I am made of atoms, and atoms have this electromagnetic force inside of them, and that's what makes the pen move. So we'll talk much more about that in class. So now what you want to do is you want to review for the quiz that you're going to have in class. This quiz is going to be a little bit different from other tutorial quizzes because I probably won't give you the pictures to go with things. I'm just going to ask you some direct questions. So go look at each slide and ask yourself, what's a question Mrs. Stracuzzi might ask about this slide? Not every slide is going to have a question. So think about it, ask yourself, okay, which are the slides that she might ask me about? And it's probably going to come down to the 3 main questions on the first slide and maybe 2 other ones that I might ask you. So think to yourself, what were the 2 key things that were brought up in the tutorial? And then bring those ideas to class with you. You can bring your notes. You can't use them for the quiz, but you can bring your notes and I'll take a look at them. If you don't do on the quiz, I might ask you, before you can take the quiz again, I might ask you to see those notes. So it's good to have them done. Okay, guys, I'll see you in class.